Hello everybody, this is Chapter 20, Part 1, video of going over the notes. So Chapter 20 is electric fields and electric forces. Sort of a long chapter, but we'll break it into two parts here. Okay, so you might actually be familiar with this sort of picture. This is separating DNA in an electric field. So the goal of this chapter is to develop basic understanding of electric phenomena in terms of charge, force, and fields. So based on the mass of particles, we develop a pattern when charged particles move through an electric field. That's part of what we'll see in this chapter. So looking ahead, we're going to look at charges and Coulomb's law. It turns out that particles that have charges, plus or minus charge, are either attracted or repelled from each other. And Coulomb's law will let us figure out how much the force between charged particles might be. A comb rubbed through your hair attracts a thin stream of water, and you can actually try this at home. So the charge model of electricity explains this force. And we'll see in this chapter that charge is just a property of electrons, for example. So electrons, because they're electrons, have a certain amount of charge. So if something is negatively charged, it had to have had electrons added to it. Okay, so we'll get into this in a little bit more detail in just a minute. So we'll use Coulomb's law to calculate the force between a couple of charged particles. Or maybe you know the force, you want to figure out the individual charges, or maybe you want to figure out how far apart these charges are. All that's in this chapter. So charges create an electric field around them. So in thunderclouds, the field can be really strong and ionize the air around it. Ionize means charge up the air. Charged particles in the air in an electric field experience a force, and that's what you actually see when you see lightning. Okay, so we'll be able to calculate the electric field for several different arrangements of charge. There is an analogy to what we did with masses. So the Earth has a lot of mass. It has a gravitational field. And other masses in the Earth's gravitational field experience a force. And we saw that the weight was equal to mg. So you could think of g as being the Earth's gravitational field. So if you have mass in a gravitational field, you see a force. If you have charge in an electric field, you'll experience a force. Now, electricity is a little more complicated. Charge could either be positive or negative. Mass was just whatever it was. It wasn't ever negative mass. Okay, so we'll have some similar ideas to what we saw before. It's just electricity is a little more tricky. Okay. So the electric field inside a smoke detector exerts a force on charged smoke particles, and a force on charged particles make them move. And we'll see in subsequent chapters that moving charge constitutes a current, and that's how smoke detectors actually work. Okay. So charges and forces. The major tools in a modest lab for studying electricity include a few different things. A number of plastic and glass rods, and if we were actually doing the first lab in person, you would see this. You could actually charge up plastic and glass rods by rubbing them with either silk or wool, and you could transfer the charge to different materials, small metal spheres, insulating spheres, things like that. So what you're about to see is what we could actually do in the lab. And in the spring semester, it works really well when the air is dry. Okay, so if you have a plastic rod, they haven't been rubbed with anything, you bring another plastic rod close by, nothing actually happens. These rods are not charged. Just bring a plastic rod near a plastic rod, nothing's going to happen if there's no charge. So no special electrical properties to just uncharged rods. So we say they're neutral. That doesn't mean they have no charge, it just means they have no net charge. Each of these has billions of positive and negative charges. There's just no excess of either positive or negative charges. So they're neutral. So if you vigorously rub the plastic rod and the handheld plastic rod with wool, and that's what you're seeing in this first picture here, these have been rubbed with wool, you bring them close to each other, they repel. And you could actually see this in the lab. The glass rod you rub with silk, and they actually repel. So rubbing two glass rods is just like rubbing two plastic rods. This is with wool and this is with silk. These have the same type of charge. The plastic, same type of charge, they repel. Glass, same type of charge, they repel. So we'll see like charges actually repel. Okay. So long-range repulsive force between charges with objects with the same charge. So long-range means they don't actually have to come in contact. So this is similar to gravity as well, right? If you can hold a baseball out to the side, let it go, it's going to be attracted to the center of the Earth. The Earth and the ball are not touching while it's in free fall there, so it's a long-range force. Same thing with electricity. The objects don't have to be in contact with each other for there to be a force between the objects. So here's a little synopsis. Electric force is the force between charged objects. Gravity is also a long-range force, as I say, but it's always attractive. Sometimes the electrical force can be repulsive. We haven't seen that yet, but we will. So if you charge up the plastic rod with wool, charge up the glass rod with silk, bring those close to each other, either in this scenario, the first scenario, or the second scenario, we'll see that these are actually attracted to each other. So the assumption here is these have different kind of charges, so dissimilar charges attract each other, just like the first picture, just like the second picture. So you can explain this experiment as well by assuming there are two different kinds of charges. So we can define one sort of charge as positive, the other charge as negative. So when people are first coming up with this, electrons, we would just assign negative to electrons. There's no reason, that's just how it started and that's how it's stayed. Turns out protons are the entity that possess positive charge. So if you're an electron, you have negative charge. If you're a proton, you have positive charge. Okay, and opposites attract. Okay, the farther and farther things are from each other, the less and less the force is. Just like gravity, the farther you are away from the center of the Earth, maybe you're a spaceship, in a spaceship or something like that, the less and less the gravitational force would be. The same thing happens with electricity. So as it says here, like gravitational force, electric force decreases with the distance. It's not directly proportional. It's this 1 over r squared relationship that we've seen before. Okay, here's a question we can take a look at. A rod attracts a positively charged hanging ball. The rod is, so if this is positive, it's being attracted. This must be negative then. So the rod must be negatively charged. So when it says neutral, we haven't seen this yet. How could it be neutral? Well, there's something called induction that could possibly happen. Let's take a look at that idea. So what I've drawn here, as you can see in the rod, it's still neutral. It has the same amount of positive and negative charges, but the individual molecules could arrange themselves maybe something like this. Negative, positive, negative, positive, negative, positive. We still have a net charge of 0. There's still the same amount of negative and positive charges, but the individual molecules could shift themselves around slightly because this is positively charged. The negative part of the molecule could push itself towards the positive side, because remember, the positive charge doesn't want to be by this positively charged sphere here. So although this is negatively charged, we are no net charge, just that's choice C here, neutral. No net charge. The individual molecules could shift around so that the negative part is closer to the sphere than the positive part, and this is called induction. Okay, we induce this scenario to happen. So a little bit of a trick question. We would not have known choice C from the material that we've covered so far today. Okay. So a charge diagram gives a schematic picture of what's actually going on. So negative charge is represented with minus, just like you saw on the previous slide, and then positive charge is represented by a plus sign. Now what's actually going on here, if this is positively charged, we have removed electrons. Electrons are the charge carrier that's easier to remove. You can't really go through and strip off a bunch of protons from this rod, but you can remove electrons. So electrons have been removed from this rod. Electrons have been added to this rod. So when we actually rub the different rods, that's what happened. We were either adding electrons or removing electrons. It just depends on what the material is made out of, whether or not it's the material likes to receive electrons or likes to give electrons up. Okay, here's another experiment we can take a look at. Start with a neutral, uncharged, hanging plastic rod and a piece of wool. Rub the plastic rod with the wool, then hold the wool close to the rod. The rod is attracted to the wool. So from experiment 3 that we did before, we know that if these are attracted, they must have opposite signs. Because the wool attracts the rod, the wool must have a positive charge. Okay, so we've given electrons to the rod. Giving electrons to the rod makes the wool positively charged then, because it has a net, it's lost electrons, so it's net positively charged. So then these are actually attracted to each other. And we could have done all these experiments in lab, and you would probably be pretty amazed that it actually works out. I mean, you actually can see this happen. That's the one thing about electricity. You don't literally see the electrons being removed, but you see what happens afterwards. Okay? So visualizing charge, as I say, you can't really see what's happening, but you can see the result of it. Okay, very good. So an object becomes positively charged if the amount of positive charge exceeds negative charge. And again, this happens by removing electrons. Okay, very good. So let's sort of summarize what we have here. In the beginning, the wool and the rod are initially neutral. Does not mean no charge, it means equal amounts of positive and negative charge. Now, when you actually rub these together, negative charge moves from the wool to the rod, and that's the charge carrier, again, that's more easily movable. And what you end up with, more negative here on the rod, more positive here on the wool. Now if you want, you could kind of go through and cancel out positive, negative. Okay, that one cancels. Positive, negative, this one cancels. Let me actually do that. They don't literally cancel, but in terms of counting up these charges, they do. Okay, those. So that's how you end up with this. There's 3 more negative charges than positive charges. And you could do the same thing for the wool here. And then you can see that they're attracted to each other because opposites attract. So there is a law of conservation of charge. Charge is neither created nor destroyed. It's really just a property. If you're an electron, you have the property of having negative charge. If you're a proton, you have the property of having a positive charge. So there's no negative charge dust that you sprinkle on something and make it negatively charged. If it's negatively charged, that means it has an excess of electrons. Same thing if it's positively charged, and it has more positive charge more protons than electrons. Okay, then we can talk about insulators and conductors. So materials like metals are conductors. Electrons can easily move through metals. The wiring in your house, for example, made out of copper probably. Electrons can easily move through copper. You can't make the wiring in your house out of glass, for example. Glass is an insulator. Electrons can't easily move through glass. So in this example here, the metal sphere acquires a charge. So we've taken the plastic, we've charged it up, you touch it to the metal, now you give a place for the excess electrons to go to, and they go to the metal sphere. So again, charge a plastic rod, rub it with wool, touch a neutral metal sphere. The charge, the negative charge on the plastic, remember, negative charges don't like to be by each other. You give them a place to go by touching the metal, they're going to go to the metal, and they're going to spread out from that point. Okay, now if you put a plastic rod between the two metals, so in the first picture, the first scenario here, you touch metal, charge from the rod is going to be transferred to the metal, you give it a place to go. None of it's going to end up here though. None of it's going to end up on the second one because this is connected with the plastic rod. Electrons can't easily move through plastic. Now if they were connected by a metal rod, they would all spread out, but here it's a plastic rod and they don't. And you can see here, if you do connect this with a metal rod, electrons can go from the charged plastic to this metal sphere, through here, and then to this metal sphere. And they spread out, they don't like to be by each other, so you'll have some charge on this sphere, some charge on this sphere. Okay. So charge can be transferred from one object to another. Up here at the top, charge can be transferred from one object to another only when the objects touch. You could actually, if you had a big enough electric field, have some electrons discharge just through the air. You don't really think, you think of air as there's nothing there, but there actually is a substance there when there's air around it. So if you have a big enough electric field, you could have a discharge, like for example with lightning. So discharging is removing a charge from an object, which you can do by touching. Okay, so what I was talking about up here is air is actually touching, so you could have electrons go through air if the electric field was big enough. So conductors are materials where charges easily move through. Insulators are objects where it's not so easy, and glass and plastic are good insulators. Metal, on the other hand, is a good conductor. Electrostatic equilibrium is the condition in which charges on an isolated conductor are in static equilibrium. They're not going anywhere. So charges are there, they're not moving. Later in the semester, we will have charges moving, and we'll see that moving charges, that's what current actually is. Okay, so we start the semester with electricity talking about this, static equilibrium, charges not moving around. And this is an example of polarization. You bring this charged rod, so this must be a glass rod, I guess, because it's positively charged. You bring it by the sphere. Negative charges in the sphere want to be here by positive charges. They're attracted. That leaves positive charges over here. The negative charges have moved away and distributed themselves in this way. Okay, so this is still neutral. It's just we've got negative and positive, and they're spread out. So this would actually be attracted. So you bring this glass rod close, don't touch it. Charges distribute themselves on the sphere like this, and then the sphere is actually attracted to the rod. Well, why is it attracted if it's still neutral? Well, the negative charges here are closer to the glass rod than the positive charges on the other side. So closer means the force is greater. So there's a net force on the sphere upward. This vector is bigger than this vector. Okay. So the polarization force arises because the charges in the neutral object are spread apart, and as you can see from the picture, closer means greater force. Okay, so whenever you have polarization like this, you have an attractive force. So next section, charges, atoms, and molecules. So an atom has a densely positive nucleus, as you can see here. Nucleus is pretty small, so this is a nuclear size. This is the atomic size, 10 to the minus 10th meters. So you think of the nucleus as being closely packed together, held together by nuclear forces, right? Positive charges don't like to be by each other, so what's holding them together? It's a nuclear force. And you could think of electrons as being out here in a cloud. Okay, so charge, like mass, is an inherent property. So if you are an electron, you have the property of having a certain amount of negative charge. We'll see that in just a minute. Same thing with protons. Okay. So electrons and protons, those are the basic carriers of charge. No other sources of charge. So protons and electrons. So an object is charged when it has an unequal number of protons or electrons. So if you have more electrons, you're negatively charged. More protons, you're positively charged. Okay, and if you have equal amount, the object is neutral. So you gain, as I said before, if something's positively charged, it's lost electrons. It's hard to remove protons from something. Electrons are the entity that you can actually remove or add. So ionization is when you actually lose electrons, or so negative ion here. You've actually gained electrons here. Positive ion, you've lost electrons. So you've lost an electron. Here you've gained an electron. It just depends on what the substance is. You probably know that from chemistry. When things become ionized, they're either positively or negatively charged. And it just depends on the nucleus. So an atom that's missing an electron is called a positive ion. Atoms that can accommodate an extra electron become negative ions. And you can see that from this picture here as well. Count up the amount of negative and positive charges. Okay, good. So the symbol Q is used for charge. We had M for mass. We have Q for charge. Now be careful, because the unit of charge is a coulomb. So you can see how that could become confusing, because charge starts with coulomb, or charge starts with C rather. So Q is used for charge, and the unit of charge is a coulomb. So the fundamental charge is this. Again, you might have seen this from chemistry as well. So 1.6 times 10 to the minus 19th coulombs. So if you're an electron, you have negative 1.6 to the minus 19th. If you're a proton, you have plus 1.6 to the minus 19th. Sometimes you might see it written like this, by the way. E minus, so this is for an electron, minus 1.6 to the minus 19th. E plus, sometimes you might have seen it like that. That's for a proton. So this is electron, and this is a proton. And it's the same magnitude of charge. One is positive and one is negative. So they contain the same amount of charge, magnitude-wise, but a proton is much more massive than an electron. So this is what we saw back in physics Ch20, maybe the masses of protons and electrons. Here we could add the charges. So this, again, that's just a fundamental property of a proton, fundamental property of an electron. So you're never going to have a charge of, say, 2.4 to the minus 19th on any object. That would be some kind of 1.5 charge, and it doesn't come in halves. You could have 1.6 to the minus 19th, 3.2 to the minus 19th, etc. So it always has to be a multiple of 1.6 to the minus 19th. Right? There's, again, nothing other than that. So insulators and conductors. Electrons in an insulator are tightly bound to positive nuclei and don't move around easy. Okay? So things, again, like glass, plastic, any object like that, objects where electrons can more easily move are called conductors. So arrangements like this, where you have outer electrons that are weakly bound, so valence electrons, and they can more easily move around in the metal, and they actually move through here. So detached from parent nuclei and free to wander through the entire solid, creating a sea of electrons. That's how you can think about it. There's a whole bunch of electrons in reserve, and if you put them in the presence of an electric field, you can guide them through metal. Now, in the beginning of this semester, again, we're going to look at electrostatic equilibrium, where things are not moving, and then later on we'll get to the point where they're actually moving. So we're really starting on the microscopic scale in this class, and then we'll move up to more of a macroscopic way of looking at the world. So Coulomb's law, finally. Here's the formula. Force of 1 on 2, which is equal to the force on 2 from 1. Remember, that's Newton's third law. K, Q1, Q2 divided by R squared. So K is a constant, and you can see it down here, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. So this is the force between charged particles, and it's again a third law pair. This constant, Q1, so that's the first charge, Q2, that's the second charge, divided by the distance between them. That's what R squared is. Not like the size of the charge or anything like that. R represents the distance between them, and it's squared in the formula. So it looks just like Newton's universal gravitational force law, where we had big G, m1, m2 divided by the distance between them squared. Here with electricity, it's a different constant, K, Q1, Q2 divided by the distance between them squared. So charges are measured in coulombs. Here's the constant, and here's the distance between them measured in meters. Okay, good. This does not tell you the direction of the force. If they are like charges, then the force is repulsive. If they're opposite charges, the force is attractive. Okay, so you have to remember that. Here's what the force looks like, graphed versus R. So it drops off like 1 over R squared. That's why you see it looking like this. Remember, it's not proportional to, inversely proportional to 1 over R. It's 1 over R squared, so it drops off really quickly like this. Okay, good. So a big part of this chapter is using Coulomb's force law, and believe it or not, you're using it right now. If you're watching this, electrons are participating in this whole event, and it all comes down to this fundamental idea that like charges repel and opposites attract. So you're using electricity right now, and you're using this whole idea. It's one of the 4 fundamental force laws, this law that you see here. Okay, great. So here's a couple of like charges, and they repel each other. Here's the distance between them. So if you knew what Q1 and Q2 were, you could figure out the force between these. So the force from 2 on 1 is the same as the force from 1 on 2, magnitude-wise, opposite in direction. These are also like charges. This happens to be both negative, so these actually will repel each other. These, negative and positive, will attract each other. Okay, great. So this is just to show you the similarity. This is what I'm writing here, M1, M2, Newton's gravitational force law. This was what we did in physics 220. Here, with electricity, it looks the same in form. Constant, Q1, Q2, distance between them squared. So you can see the similarities. We had a constant, here you have a constant, M1, well, this was for mass, this is for charge. M2, Q2, distance between them squared. Okay, so this was the first fundamental force law that we saw in physics 220. Now we have this one for physics 221. Okay, very good. Making some real progress in the physics world. So Coulomb's law is a force law. The forces are vectors, as you know, so you'll have to figure out the direction based on whether they're like charges or opposite charges. And then there can be more than one force, right? Just like we did in physics 220. So to figure out the net force on something, you have to add up all the forces. Now you don't just take numbers and add them together. You add all the x parts together. You add all the y parts together. Some might be positive. Maybe a force to the right is positive. A force to the left is negative. A force up is positive. Force down is negative. So you have to add all the x parts together, all the y parts together. And you've done that before in physics 220. Okay, let's take a look at this one. The direction of the force on negative q is, okay, so the force on this negative little q is from a contribution from negative big Q and plus big Q. And we want to know the direction of the force on this charge. Okay, so for a minute, pretend that plus big Q is not there. This is negatively charged, this one's negatively charged. So we're going to have a force this direction from minus Q, minus big Q on minus Q, right? Those are opposites, so they're repelling. So this one is being repelled. Minus little q is being repelled by minus big Q. Now pretend minus big Q is not here. This is positively charged, this is negatively charged. So minus Q is going to be attracted. So there's going to be a force from plus Q. Let me see if I can write this a little bit better. Plus Q on minus Q. There we go. So the net force then, this one is larger than this one, so the net force is going to be that direction. Minus big Q is repelling, plus big Q is attracting. Minus big Q, though, is closer to minus little q, so it dominates. That's why I drew it larger here. So to the right, minus q is slightly closer than plus q. Okay, very good. Let's take a look at this one. We've got 2 plus 10 nanocoulombs. So remember, nano is to the minus 9th. So plus 10 nanocoulomb. Charged particles are 2 centimeters apart. Okay, that's perfectly good. It's not in meters, so be careful with that. On the x-axis, what is the net force on a plus 1 nanocoulomb charge? So what's the force on this charge midway between them? And then what is the net charge if the charged particle on the right is replaced by a negative 10? Okay, so we got a plus 10 here and a plus 10 here in the first picture. What direction is the force if you put a plus charge here? Well, you can see in the first part here on this Q3, so this one is plus 1. Okay, so plus 10, plus 10, plus 1. Luckily, in the first scenario, we don't have to do any calculating if we draw the picture correctly. So there's a force from 1 on 3 to the right, this direction, as you can see. There's a force from 2 on 3 this way, right? They're this direction that I'm drawing it because they are same charges, like charges, and they're repelling each other. Q1 and Q2 are the same magnitude. This is the same distance. These actually cancel out. So there is no net charge. Okay, in the second scenario, this is positively charged, this is negatively charged. Q3 is positively charged. So 1 is going to repel 3, as you can see here, right? This is positive and this is positive. Q3 does not want to be by Q1, so there's a force that way. This is negatively charged now. We've switched it to negative 10 nanocoulombs. This is positively charged, so the force is going to be this direction. And they actually work together here. So from the perspective of Q3, it's being repelled by Q1, it's being attracted by Q2. Those are in the same direction. They're actually going to add together. So let's actually solve this problem. Okay, so here I've written this in equation form here. This is force from 1 on 3. This is force from 2 on 3. Now, this is the first time we're doing an equation, putting numbers in this semester, so it's kind of exciting. Here it's from Coulomb's force law, K, magnitude of Q1, magnitude of Q3, that's 3, divided by the distance between them squared. Then we have K, Q2, Q3, magnitude of those, divided by the distance between them squared. Now the distance between them is 2 centimeters. We need it in meters, so divide by 100, 0.02 meters. The magnitude of Q1 and Q2 are actually equal to each other, 10 nanocoulombs, or 10 times 10 to the minus 9th coulombs. Q3 was 1 nanocoulomb, or 1 times 10 to the minus 9th. Remember, a coulomb is very small. An electron is to the minus 19th coulombs. So this might look like it's pretty small, but it's like 1 billion times more than 10 billion times more than an electron. Okay, and then we just have to put the numbers in here. So let me actually do that here. F net K. So I'm just going to do 9 times 10 to the 9th newtons meters squared over coulombs squared. It's 8.99, but 9 is practically the same thing. Okay, and then magnitude of Q1, which is 10 to the minus 9th coulombs. Magnitude of Q3, 1 times 10 to the minus 9th coulombs, divided by the distance between them squared. So make sure you put it in meters. Don't forget to square it. So you'll see that this is going to come out in meters, right? We've got meters squared and meters squared. That cancels. Coulomb squared, there's a coulomb and coulomb. So that's this part, plus K, 9 times 10 to the 9th, newtons squared, coulomb squared. That's what K is. Q2, 10 to the minus 9th coulombs. Q3, 1 to the minus 9th coulombs, and then divided by the distance between them squared. Okay, so put that in your calculator, and you should come up with the answer. Whoops, you didn't see the very bottom part. 0.2 meters. Okay, very good. So we're adding those together because they're working in the same direction. So why don't we actually do this one time, just at the beginning of the semester, just to refresh your memory. So here's my calculator. Yours might be more complicated than mine, but it's okay. So 9 times 10 to the 9th. Right, that's what I have to punch in here. So I would do 9, and then my calculator has this EE button, which means times 10 to the, and then I could put in 9th, and then times 10 EE minus 9th, 10 EE minus 9th. That means 10 times 10 to the minus 9th times 1 EE minus 9th. So I'm using the minus here, not the subtract button, divided by 0.02 squared. That's the first part. That's this part. And then really I'm just putting the same thing in again. So if I just take what I just did and multiply it by 2, that would give me the same thing. I mean, you could punch this whole thing in again if you want to. I'm just going to multiply what I have by 2, and I'm doing that because, again, this and this is going to give me the same thing. I'm just doing the same thing again. So times 2. So 0.00045 newtons. 1, 2, 3, 4. 4.5 times 10 to the minus 4th newtons. That's the net force. Now you might say, that's a very small force, and it is small, maybe if you think about it, to the minus 4th, but this could be a force on, something that has very small mass, so this would maybe really experiencing it. This on us would not feel like anything. This on an electron would be really, really large. Okay, let's continue. Okay, so which is the direction of the net force on the charge on the lower left? Okay, so the charge on the lower left, we have several different choices here. Actually, it's kind of given away because this one's a different color, but we'll work it out. Let's look at it from thinking about, let's just pretend that this is the only charge that's causing a force on this one. So we're looking at the direction of the force on this charge, the one on the lower left. Okay, so let's look at the contribution from each of these individually. Let me just call this one 1, 2, 3. Okay, the force from 1 on this charge would be this direction. Really, this is the direction of the force if we just had 1 there. This is the direction of the force if we just had 3. So this would be from 1, this would be from 3. Because they're like charges, they're repelling. This would be the direction of the force because of 2. Now if you were to add all those up, 3 pushes it to the left, 1 pushes it down, 2 is pushing it this way. So the net force is actually going to be in the same direction as 2 here, right, if you added them all together. Okay, so this one's actually the direction of the force. This positive charge here at the lower left is being pushed away by all of these, 1, 2, and 3. And then the net direction then is going to be down this direction. Okay, like charges repel. Okay, here's another one we can take a look at. A small plastic sphere is charged to -10 nanocoulombs. It's held 1 centimeter above a small glass bead at rest on a table. The bead has a mass of 15 milligrams. Okay, so be careful, milligrams is really, really small. And a charge of 10 nanocoulombs. Will the glass bead leap up to the plastic sphere? Okay, so let's read it again. Sometimes you've got to read these things a couple of times. A small plastic sphere is charged to -10. That's what we have up here. That's the plastic, charged to -10. It's held 1 centimeter above a small glass bead that's at rest on a table. Okay, so here's the glass on the table. The bead has a mass of 15 milligrams. Will the glass bead leap up to the plastic sphere? Okay, in other words, is the electrical force greater than the weight? So, negative charge, positive charge. There's an electric force between them. Is that electric force going to be larger than the weight? If the electrical force is actually larger than the weight, then the glass bead will leap up to the plastic sphere. Okay, so let's work this out and see how much the weight is and see how much the electrical force is. Electrical force bigger than weight, it will leap up. Okay, let's take a look at it. Okay, so what I have here is Newton's, Coulomb's force law, K, Q1, Q2 divided by the distance between them squared. That's Q1, that's Q2, that's the distance between them squared. We can figure out the electrical force. I'm just calling it force electric. It would be 9 times 10 to the 9th, Newtons meters squared over Coulomb squared. That's what K is. Q1 is 10 to the -9th coulombs. That's the magnitude of it anyway. Q2, 10 to the -9th coulombs. And then the distance between these charges, the beads and the plastic, this amount. We can figure out how much the electrical force is then. We have 9 to the 9th times 10 to the -9th times 10 also to the -9th divided by the distance between them, 0.01, and then don't forget to square it. Okay, enter. 0.009 newtons. That's the electrical force between them. Now, is it greater than the weight? Let's figure out the weight. The weight is equal to mg. Just be careful with the mass. It's 15 milligrams. We need it to be in kilograms. So 15 milligrams, 1,000 milligrams is 1 gram. That's not good enough, though. We need it in kilograms. And then 1,000 grams make up 1 kilogram. So that's pretty small. 15 to the -6th in kilograms. Right, milligram cancel out, gram and gram cancel out. Okay, so 15 to the -6th, if you did this in your calculator, it would probably give you 1.5 to a different power here. So if we make this one smaller, we got to make this one bigger. So it would be 1.5 to the -5th. But again, you don't have to do that. I'm just going to leave it like this. So mass, 15 to the -6th kilograms. And then G is 9.8 newtons per kilogram. Let me actually do this then. So 15 to the -6th times 9.8. 0.000147. Electrical force, bigger than the weight, it actually leaps up towards it. Okay, good. So that's pretty neat. That's if you actually had this situation, you would have them come into contact with each other. You overcome the weight. This number, 9.8 newtons per kilogram. Well, didn't we used to wasn't it meters per second squared? It's the same thing, a newton per kilogram. Let me show you why. Meters per second squared. What if I multiply the top and bottom of this by kilograms? Right, this meters per second squared, that's what we used to have by 9.8. It was 9.8 meters per second squared. But if I multiply the top and bottom of this by kilograms, which I can do, that's just like multiplying by 1, I get kilogram meters per second squared, and then I still have another kilogram here. So I've just rearranged this. Kilogram meter per second squared per kilogram. A kilogram meter per second squared is in newtons. So really, we were doing this all last semester. We thought about it as acceleration due to gravity, but it's also the strength of the Earth's gravitational field, newtons per kilogram. All right, pretty cool. Okay, so what we've covered today is really looking at the fundamental idea of charges, electrons, protons, and then we have we didn't discover it, but we played around with Coulomb force law. So we saw that the force is equal to some constant, K, and then the magnitude of Q1, magnitude of Q2, divided by the distance between them squared. And we did a couple of examples. The homework has more work with that. So make sure you're reading through the chapter, and then I'll make another video with the second half of this chapter. Any questions, just email me. Talk to you soon. Bye-bye.